In the previous video, we learned two basic criteria for to evaluate estimators. To which estimator is good, we are going to think about these two criteria. Okay, so then I'm going to study each of them. First, we are talking about the unbiasedness. We will learn about the unbiasedness criterion. So as I said, theta hat is an estimator and theta is a true parameter. So their difference is the estimation error. And because theta hat is random, the estimation error is also random. Sometimes you are going to get like positive error, sometimes negative error, sometimes large, other times small. So it is random. And we know overestimation is when the error is positive. Like estimator is greater than the true parameter. And underestimation is when the error is negative. So that is unavoidable. Like it happens. Sometimes it will be positive, other times it's negative. So we cannot make it always zero. That is impossible. But what we want is, on average, we want they are balanced. So like for example, 50% you overestimate, then we want 50% underestimate, and so that they can cancel out. So we will take the expectation of the estimation error. Because it is random, we can think about its expectation. So like this is the expected value of the estimation, right? And the difference from the true parameter is the bias. If the bias is positive, then the estimator on average tends to overestimate. So the expected value of the estimator is greater than the true parameter, so means like on average overestimation, and vice versa. If it's negative, then the expected value is smaller than the truth, so it tends to underestimate. So ideally, we hope the bias to be zero. Then we say the estimator is unbiased. That is the ideal, the desirable situation, right? So we call unbiasedness criterion. So, and as you see, these two graphs, these two estimators compare the bias. So the orange estimator is expected to be here, which is greater than the true parameter. So it has positive bias, positively biased toward the larger size, right? Overestimating on average. But the blue is well balanced, so it is unbiased and expected to be correct on average. That is intuitive. So this is the first criterion, which is very intuitive, and it is about the expectation. Okay. Now, what is a little more tricky is the second one. And the name for the second criterion is efficiency. But it is related to the standard deviation or the variance of the estimator. Say, like as I said, theta hat, the estimator is random. So we can think about its standard deviation. Specifically, the standard deviation of an estimator is called the standard error, right? So because it is based on the estimation error. Okay, so then we want the standard error to be small. The smaller the better. Always the smaller the better, right? So if you repeat the estimation again, so in doing this, the underlying experiment is another random sampling. So one experiment consists of like this: if random sample and then calculate the estimator and compare that with the true parameter, and you get estimation error. That is one experiment, right? And if you repeat, that means you are going to draw a new random sample and recalculate the estimator and recalculate the estimation error. That is another observation. If you repeat that, if the estimator realization of the estimator is variable, like spread out too much, then your estimator is unreliable. But if results are close to each other, and then you can just believe that the truth will be close to it, where those estimators are. So then you can think that estimators are reliable. So it is related to standard deviation or the standard error. So, and by the way, as I said, it is just the smaller the better. The smaller the better, but technically it is impossible to have zero standard deviation. Having zero is impossible. So the criteria, the efficiency criterion is a relative criterion. So you need to have two estimators and you are just comparing them. Say, so it is hard. So it is, I don't say one is efficient, but I usually say one estimator is more efficient than the other. So it's relative by comparing the standard deviation, and like the smaller is the better one. That's how we use the second criterion, the efficiency criterion, right? And as you see, the efficiency criterion is like this. Like, so if the sampling distribution is variable, spread out, dispersed, then your estimator can be like anywhere, far away from the true parameter. So it is unreliable and inefficient relative to the blue estimator, which is concentrated around the true parameter. So usually closer to the true parameter with a higher probability, right? So blue is more efficient than green estimator. Then you may wonder, why do we call this efficiency, not like, reliability or something else? I would explain that this way. So in the previous chapter, we learned the variance or the standard deviation takes this form. So standard deviation of x bar equals the standard deviation of a single outcome divided by square root of n, right? You remember? So the standard error depends mainly on the sample size. So simply speaking, if you increase the sample size, you get more efficient estimator. Otherwise, if you cannot fully utilize the information in your data, then your estimator is inefficient. So the standard deviation of an estimator depends on how efficiently you utilize the information. Like if you have 100 observations, you have to efficiently use all of them, extract all the information in the data. Otherwise, for example, if you throw away some of them, you are not efficiently using the data, so your estimator will have larger standard deviation. So we call that inefficient. So that is, I guess, this is my guess, why this criterion is called efficiency. So it is related to efficient and full use of fully utilizing the information in the data. Okay. By the way, so as I said, it is not easy to see what is the minimum efficiency, like, right? So like when one have larger sample size than the other, the decision is usually easier. Using more sample size is better, right? However, when you have the same data among two estimators, how can you compare? That depends on, you need to calculate the standard error. It's a more theoretical result. For example, how can you compare the mean and the median? For example, you are estimating normal distribution's mean, and you may use the mean or the median from the sample. Which is more efficient? We don't know, if as long as they have the same sample size, but technically, mathematically, you can calculate that the standard deviation of median is larger than the standard deviation of the sample average. In this sense, sample average is a more efficient estimator than the sample median, right? When you estimate the expectation, okay? So this is how we compare efficiency when you have the same sample size, and this is actually more difficult than comparing the sample size, of course. But so simple summary. I would like to compare, use analogy of this estimation to, shooting or like archery. So the ideal among these four cases, the ideal like results is like this. The target is exactly centered at the center of the at the bullseye, right? The center is correct. So we say it is unbiased. The target is exactly correctly centered, and also your target does not move that much. It is consistently at the center, right? So in that sense, it is efficient. So let's compare this outcome with this case. So on average, you shoot 5 bullets, and they hit different places. But on average, it seems like on average they are correctly centered at the bullseye. That is right. But the problem is the target moves a lot, right? So maybe because of the recoil. So sometimes you hit there and it goes there and there. So that is so the center is correct. The center of the target is correctly aligned, but the deviation is, the variability is larger. So this result is inefficient. This shooting, maybe this gun, is inefficient than this one. Okay, now let's think about this one and this one. The variation is not that different, but the problem of this result is that the target is not correctly centered. It's not exactly aligned with the bullseye. So it is shooting at here, away from the center, right? So the problem of this gun, this maybe machine, is the 0 point is away from the bullseye. So it is about bias. Efficiency is okay. So the variation is correct. Is it does not deviate that much. So in that sense, that is good. But center is not correct. So it is biased. And this is the worst, of course. The center is away from the bullseye, and also it moves a lot. So this is inefficient and biased. So worst outcome, worst estimator. Okay, so I think this is a simple analogy and easy to understand compared to the estimation problem. Okay, so now let's apply our criteria to specific cases. In the case where we are estimating the population expectation, so we have random variable. If we could observe infinite number of this random variable, then we can calculate the population expectation, which is denoted as Greek letter mu. But of course, we can't observe infinite observations. Then how can you estimate that? Simply speaking, the conclusion is that the sample average is the best estimator, right? So sample average x bar is calculated. This is the average, and we learned in the previous chapter. We learned the expectation of the sample average is the same as the true expectation, right? So unbiased. And standard error of this estimator is like this, and mathematically we can show that this standard error is the minimum possible standard error we could achieve to estimate the mean. So mathematically, there is a theorem saying that the sample average is the best estimator. In mathematical statistics textbooks, they call this the minimum variance unbiased estimator for the population mean, right? Simply speaking, this is the best estimator. So that means there is no other unbiased estimator with smaller standard error. So among the unbiased estimators, this is the best, smallest possible standard error mathematically. Okay, so you don't need to know the theorem, but point is, whenever you need to estimate the population mean, you don't need to think of any other estimator but just the sample average. This is mathematically the best. It's not because it is population mean and this is the sample mean, not because of their name, but based on our criteria, this is the best, mathematically the best. Okay, this is how statisticians evaluate estimation and propose like better estimators. Okay. Then now, another example is estimation of the variance, right? By the way, back in chapter 4, we learned two formulas for variance, sample variance. One was population variance formula, and the other was sample variance formula. By the way, it can be confusing. So, if you calculate the variance using infinite number of observations, we are going to call that population variance. If you calculate variance using your sample, then we are going to call that sample variance. So the name of the formula doesn't mean the same population variance or sample variance. They are just they happen to have the same name, but both are based on sample. So when you calculate the sample variance, there are two formulas. One is population variance formula, and the other is sample variance formula. By the way, anyhow, at the time, I suggested the sample variance formula is more common. And the reason, at the time I said, I cannot explain that at the time, right now. But now I can do it. So simply, the sample variance is unbiased. But the sample variance formula is unbiased. But population variance formula is biased. So mathematically, you can show that if you use n, by the way, the difference is denominator, whether denominator is n or n minus 1. If it is n, then you have this much like term mathematically. So because n minus 1 over n is smaller than 1, so it underestimates the population variance formula, underestimates the population variance, right? So it is biased. It's negatively biased, underestimates. But to adjust that, you have to cancel out this much. So by changing the denominator to n minus 1, now you have unbiased estimator for the true variance. This is the reason why the sample variance is used. But actually, so imagine this, like in the end, if in practice, if n is large enough, n minus 1 over n is very close to 1, right? If n was 100, it is 99 over 100, which is 0.99. So it will be very close to 1. So practically the difference is really, really small. So it does not matter that much even if you use the population variance formula, right? That is okay. I'm not saying that is wrong, but you have to understand that it is underestimating the variance. Okay, that's what I wanted to say at the time, but I couldn't. Okay, so intermediate summary. So far, we learned basic framework for statistical inference, like distinction between population and sample, and parameter and statistic. So you need to understand their differences. And then we learned what the requirement for a parameter and an estimator. And what's more important is when you have multiple estimators, how can you tell a good estimator? I suggest two criteria, unbiasedness and efficiency. Okay? And based on these two general criteria, if you apply these two criteria in the estimation problem for population mean, we can conclude that the sample average is the best estimator based on these two criteria. Okay? So these are this is simple summary, and in the next video we are going to extend our estimation framework. So far I just said this is the best, but another important step in practice is to evaluate the accuracy of that estimator. I know this is the best, but still it can be wrong. then how much can it be wrong? That is another natural question we need to answer. That's what we are going to do next time. Okay, see you later.